Hello everyone, now we will have a tutorial session and in this class we will solve some numerical problems based on our discussion made in the last 4 classes. Problem number 1, the statement is a country discards roughly 158 million tons of MSW. The high heating value of those discards is about 6000 BTU per pound. A mass burn waste to energy facility can convert those wastes to electricity with a heat rate of 17000 BTU of thermal input per kilowatt hour of electrical output, roughly 20% efficiency. Estimate the electrical energy that could be produced per year if all the discards were used in this type of WTE system. Compare it with the total energy generated, which is about 4500 into 10 to the power 9 kilowatt hour per year. So, this is the problem statement. Now, we have to solve. So, what we will do? We will see that what is the electrical output we can get from this waste and then total electricity production which is provided here. So, we will be take the ratio of that. So, electrical output that equal to how much it will be? We are using 158 million tons of MSW. So, this 158 into 10 to the power 6 ton per year. So, that is million to this 10 to the 6 ton per year into then we are multiplying it by 2000 pound per ton, because this is unit conversion. So, ton to pound. So, this is multiplied by this 2000 and then what we will do? The heat content of it. So, now we are getting the total waste generated in pound unit. So, then we will multiply it with the heating value, that is 6000 BTU per pound. So, now which we are getting, that will be in BTU unit per year, but we need kilowatt hour per year. So, then 1 BTU, that is it is given here that the heat rate of 17,000 BTU of thermal input per kilowatt hour of electricity. That means, for the production of 1 kilowatt hour we need 17,000 BTU. So, then we have to divide it by 17,000 BTU per kilowatt hour. So, then it is we are getting 111.5 into 10 to the power 9 kilowatt hour per year. So, this is the electrical output which is generated by the consumption of this amount of MSW. So, first part we have got the answer, then second part we have to compare it with the total energy generated, that is equal to this one 4500 into 10 to the power 9 kilowatt hour per year. So, this is the production. So, 115.5 into 10 to the power 9 kilowatt hour per year and this is total production. So, this is the energy from waste to energy conversion and this is the total energy production in the country. So, then we will get this is the fraction. So, multiply it by 100. So, that will be in percentage. So, 2.4% is in percentage. So, total energy consumption. So, 2.5% of the total energy consumption is coming from this waste to energy plant. Okay. So, now we will move to problem number 2 and the statement is estimate the landfill area needed to handle 1 year's MSW for a town of 2 lakhs people. Assume per capita national average discards of 5 pounds per day. No combustion, a landfill density of 1000 pound per yard cube and 1 10 feet lift per year. Assume 20% of the cell volume is soil used for cover. So, this is the problem statement. So, now we have to find out the area requirement for this landfilling. So, at first we will calculate the volume of the MSW, then we will see the volume of the cells, then lift is given. So, from that we will get the value of the area requirement. Okay. So, now let us see the volume of MSW. So, volume of MSW is equal to mass of MSW divided by density of MSW. So, mass of MSW can get total number of people and the generation per 1 persons. So, that is 5 pounds per day per person. So, 5 pounds per day per person that we are getting into 365 day per year. So, this is per year per person production of waste, and we have this number of total people. So, we will multiply this 2 lakhs. So, this the numerator term is the total waste generated, the mass of the waste generated. Then we will divide it by the density of it. So, we will get the volume. So, then we are getting 365,000 yard cube per year. So, this is our total volume of the MSW. Now, it is given that 20% of the cell volume is soil used for the cover. So, 80% is MSW and 20% is the volume of the soil which is used for this purpose. So, this is MSW volume. So, what will be the cell volume? We have to divide it by 0.8, that means the cell volume will be more than the volume of the solid waste. So, then that is 365,000 yard cube divided by 0.8, that is equal to 456,250 yard cube per year. So, this is the volume of the cell. So, which is used to discharge the MSW for 1 year. Then per year lift it is given 10 foot lift per year. So, the area of the lift per year of 10 foot per year of depth, that will be, so area into lift, that is equal to volume of the cell. So, area is equal to volume divided by lift. So, here it is given 456,250 yard cube per year we have got. So, we are interested to convert it now into feet cube. So, then this is the unit for the conversion of yard cube to feet cube. So, 27 feet cube per yard cube. So, this one. So, that is now we are getting feet cube per year and our lift is 10 feet per year. So, we will divide it by 10 feet per year. So, then the value we are getting by this expression is 1231875 feet square. So, this is the area which we are getting from the calculation, and volume also we are getting, but actually the area requirement will be more, because there are some additional activities which will be associated with the active filling. So, the actual sizing of a landfill would include a number of additional factors such as additional area requirements for access roads and auxiliary facilities, reduction in landfill volume as biological decomposition takes place, and increases in compactions as additional lifts are included. So, because of this the actual requirement will be differed to some extent from this one, and it will be more than this. Now, problem number 3. The statement is wastes such as tires can be disposed of using a process known as pyrolysis. A car tire has a mass of 20 kg, 47% by mass of a car tire can be converted into carbon and 25% by mass can be converted into gas, which is mainly methane. What volume of methane at room temperature and pressure is produced in the process if 80,000 tires are treated through this process? So, this is a problem statement of a pyrolysis process. Waste tire is converted to different pyrolysis products, and it is assumed that the gas which is produced only methane is present to make the calculation more simple. So, here we will have to do some mass balance. So, let us see mass of 80,000 tires, that is equal to 80,000 into 20 kg, that is into 20 into 1000 gram. So, 16 into 10 to the power 8 gram. So, this is the mass of 80,000 tires. Now, 25% of this is converted to gas. So, 25% of this is equal to 25 into 16 into 10 to the power 8 divided by 100. So, that is equal to 16 into 10 to the power 6 gram of methane. Now, molecular mass of methane is equal to 16 gram. So, moles of methane is equal to this much 25 into 16 into 10 to the 6 divided by 16. So, 25 into 16 by 16 into 10 to the 6 mole. So, that is equal to 25 into 10 to the 6 moles. Now, 1 mole occupies 22.4 liter or decimeter cube volume at NTP, we know it very well. So, volume of this moles of methane will be 22.4 into 25 into 10 to the 6 decimeter cube or liter. So, that is equal to 5.6 into 10 to the power 8 liter, and that is equal to 5.6 into 10 to the power 5 meter cube. So, this is the volume of the methane which is generated to this pyrolysis. Now, the room temperature is 30 degree centigrade. So, volume will be 30 plus 273. So, 303 divided by 273 into 5.6 into 10 to the power 5 meter cube, that is equal to 6.215 into 10 to the 5 meter cube. So, this will be the volume of methane at 30 degree centigrade. This we can get, that is equal to P 1 V 1 by P 1 V 1 by T 1 equal to P 2 V 2 by T 2. So, here P 1 and P 2 both are same in this case. So, by using this formula we are getting this the volume of methane at 30 degree centigrade. Now, problem number 4. The statement is, in an MSW gasifier, air flow rate and feed flow rate are 10 normal meter cube per second and 8 kg per second respectively. The MSW does not contain any sulfur, nitrogen and chloride. The syngas contains carbon monoxide 40%, CO2 2%, H2O 30%, CH4 5% and C2H2 2%. Calculate the rate of production of syngas in normal meter cube per kg of MSW. So, again this is another problem related to the handling of MSW through gasifier, and through the gasifier we know that producer gas or syngas, when we use the oxygen we get syngas and when we use the air we get producer gas. So, this is the case of producer gas production. Now, what we will see, this is also again can be solved on the basis of mass balance of nitrogen. So, we know that if the fuel gas production normal meter cube per kg, so this is, so in the fuel gas what will be the nitrogen production or the nitrogen available in this fuel gas. So, this is the production rate into the nitrogen concentration of it. You see the CO, CO2, H2, CH4, C2H2, these are the gas components present in the producer gas. So, 100 minus this if we take, so that will be nothing but the nitrogen which is available in it and it is coming through the air we are using for it. So, this nitrogen into this and feed rate, that is normal meter cube per kg. So, this kg per second. So, that will be the normal meter cube per second unit we are getting the fuel gas production. So, right hand side in that case we will get air flow rate, that is normal meter cube per second into 0.79, because 79% of volume of the flue gas or air we are getting here air flow rate, the nitrogen this is output and inlet is this one air flow rate. So, air flow rate into the 0.79, that is the percentage of nitrogen present in the air. So, this is the total volume of nitrogen present in the air and this is volume of nitrogen present in the fuel gas. So, this expression is just on the basis of nitrogen mass balance. So, now we will be putting the values provided here. So, in this case we are getting 10 into 0.79 air flow rate. What is the air flow rate? 10 normal meter cube per second. So, 10 into 0.79 divided by 1 minus 0.4, 0.02, 0.3, 0.05, 0.02. So, this is the fraction of it. So, different gas components and then this has to be multiplied by the feed rate, that is equal to 8 kg per second. So, this is the syngas production. So, we are getting by solving this at 7.9 into 0.1 into 8, that is equal to 4.702 normal meter cube per kg MSW. So, this is the syngas production. Okay. So, now we are able to solve the problem. Next problem, statement number 5. A pyrolysis plant handles 0.5 TPD MSW and produces gas, char and liquor. Operating temperature is 788 degree centigrade and pressure of the reactor is 1 atmosphere respectively. The gas composition volume percent is H2 39.10, CO 33.50, CH4 13.10, CO2 14.3. The mass percent of production of gas, char and oil are 35, 20 and 45 respectively. Determine the number of moles of each component of gas produced per day. So, we have to calculate the number of moles of each component of gas produced per day. So, this is a problem related to pyrolysis of MSW. So, here we are taking a basis that is 500 kg MSW per day. So, mass of gas produced is equal to 500 into 35% of it. So, 0.35. So, that is 175 kg per day. So, mass of char produced equal to, as it is 20%. So, 500 into 0.20. So, 100 kg per day. Mass of oil produced which is 45%. So, 500 into 0.45. So, 2 to 5 kg per day. Now, we are getting the gas which is having different components. So, average molecular weight of gas produced will be 39.10% hydrogen. So, 0.3910 into 2. So, this is 33.2, that is nitrogen. So, plus 0.335 into 28 plus 0.131 into 16 oxygen plus 0.143 into 44, that is carbon dioxide 14.3%. So, then we are getting 18.55 kg per mole. So, this is the average molecular weight of gas produced. So, gas produced in kilomole per day, that is equal to, we have 175 kg per day. So, 175 divided by 18.55 we are getting, so that we are getting 9.43 kilomole per day. So, this is the gas production per day. Now, we have to calculate individual gas molecules production per day. So, hydrogen production, so 9.43 is the kilomole total gas. So, individual will be in the same ratio. So, 9.43 into 39.1 divided by 100. So, 3.69 kilomole per day. So, carbon monoxide production, that is equal to 9.43 into 33.50 by 100, that is equal to 3.16 kilomole per day, and methane produced equal to 9.43 into 13.10 into 100, 13.10 divided by 100, that is equal to 1.24 kilomole per day, and carbon dioxide produced will be 9.43 into 14.3 divided by 100. So, that is equal to 1.35 kilomole per day. So, on the mole basis, these are the production of different components per day. So, the problem is solved now. Now, we will move to the next problem, problem number 6. The statement is, a dry MSW has the following composition on mass basis: carbon 40%, hydrogen 5%, oxygen 30%, ash 25%. Determine the stoichiometric oxygen requirement for the combustion of the MSW. Assume the ash as inert and average molecular weight of ash is 56. If the ratio of nitrogen to oxygen in air is 4:1, volume by volume ratio, determine the stoichiometric requirement of air. So, this problem is basically related to the incineration of MSW. So, we have to calculate the stoichiometric requirement of air. So, again we will take here a basis, that is 100 gram dry MSW. So, carbon is 40%. So, for 100 into 0.4, so 40 gram, that is equal to 40 divided by 12. So, 3.33 moles per 100 gram MSW carbon is present. So, hydrogen is equal to 5%. So, 5 gram. So, mole will be 5 by 1, this is equal to 5 moles, and oxygen is equal to 30%. So, 30 gram. So, 30 divided by 16. So, that is equal to 1.875 moles, and ash 25%. So, 25 gram and divided by 56 molecular weight. So, this 0.4464 moles. So, these are the number of moles present in 100 gram of dry MSW. So, we can get the average molecular formula of the MSW as C 3.33 H5O 1.875 and ash 0.4464. So, this is the molecular formula of the MSW. Now, if we take the general expressions for the incineration or combustion, so Ca, CHB, SOC, ash G plus DO2, that is giving us E mole H2O plus F mole CO2 plus G mole ash. In this case A we have got the value 3.33, B is 5 and C is 1.875 and G is 0.4464. So, this is given. So, we have to calculate the value of D. So, by doing some balances of elemental mass, that is carbon balance from both sides, hydrogen balance, oxygen balance, ash balance, etc. So, we will get some relationship with this E and these known variables, and from that relationship we will get the value of all these unknown variables, and once we will be able to find out the value of D, that the stoichiometric requirement of oxygen we will be able to calculate, and since 4:1 the ratio nitrogen is to oxygen in the air. So, from that we will also be able to know the air requirement stoichiometrically. So, now if we consider the carbon balance, so that is equal to 1 and this is F moles. So, A is equal to F from the carbon balance. If we do the hydrogen balance, so left side is B mole and 2 E mole. So, B equal to 2 E, and if we do the oxygen balance, then C plus 2 D left side and right side is E plus 2 F. So, oxygen balance. So, these are the relationship we are getting. Again A is equal to, already we have got 3.33. So, A equal to F equal to 3.33. Now, B equal to 5. So, E equal to 5 by 2. So, 2.5 and C is equal to 1.875 already we have got. So, these expressions we will put these values 1.875 plus 2 D equal to E is equal to 2.5 already we have got, and plus 2 into F, F is that is 3.33 we have got. So, then by rearranging we are getting 2 D equal to 2.5 plus 6.66 minus 1.875. So, we are getting 7.285 or D is equal to 3.6425. So, now we are able to calculate the value of D. So, 3.6425 moles will react with this MSW to get the different products. Therefore, for 100 gram of MSW oxygen requirement is this much, this moles into 32. So, that is 116.56 gram. So, stoichiometric requirement of oxygen is this much gram per 100 gram of MSW or 1.1656 gram oxygen per gram of MSW. So, this is our requirement of the oxygen. Now, nitrogen in the air containing 3.6425 moles oxygen, that is equal to 4:1 ratio. So, 4 into 3.6425. So, that is equal to 14.57 mole. So, mass of nitrogen will be this into 28 molecular weight. So, 407.96 gram. So, this is the nitrogen and this is our oxygen. So, then we will be this much of oxygen. So, we are getting the mass of air is equal to 407.96 plus 116.56, that is equal to 524.52 gram. So, stoichiometric requirement of air is equal to 524.52 gram per 100 gram of MSW. So, now we are able to solve the problem and we have seen the stoichiometric requirement of air. So, now we have solved all the problems and thank you for your patience.